I'm just going to give the screen and session to you.
Thanks very much, Lee. It's great to have this opportunity, and I'm really excited about Lee's leadership. He's a terrific intellectual leader in educational statistics, measurement, and modeling, but also by Lee's involvement with HLM, with the new VPG company, I think is really going to be a lot of fun for me, and I hope for people who are interested in HLM. We're going to be having these webinars. We're going to have frequent updates of the program. We have a lot of interesting ideas in mind. The updates come automatically to you. So this is an exciting kind of new start for HLM. And today, I want to talk about a couple of questions that are really related, but of all the questions that I've gotten over the many years of talking about HLM, running workshops, these are some of the most frequently asked questions. If HLM is a random effects model in the sense it has random intercepts, random slopes, people will ask, should I be using fixed effects, not random effects? The econometric literature really tends to favor fixed effects over random effects. So what's the difference? When should I use one? When should I use the other? And then the other question, which seems unrelated, but you'll see soon is very closely related, is centering, particularly group mean centering. Should I group mean centering my predictor variables or grand mean center? These questions typically come up, or not always, but often come up when there are causal questions on the table. So those are the things I want to talk about today. And so the scenario that we're going to be talking about today is multi-level data. We'll start with 2 levels, then we'll go to 3 levels, where, and this is really important, the key explanatory variable is at a lower level. So here's 3 examples. So in the National Head Start Impact Study, over 300 program sites were sampled from a large number of thousands of Head Start sites. And within each site, eligible people applied and were randomly assigned to be in Head Start or not in Head Start. So the treatment, which was to be in Head Start or not, was implemented within each site, okay? So each site produced a treatment effect. And another example is very closely related is meta-analysis. We have a large number of studies. Each study has some kind of an association, very often a causal effect, a treatment effect. In effect, this involves experimental subjects being nested within studies. And within each study, there's a contrast between the treated and control. And we're trying to synthesize those. We have a whole family of treatment effects. What's the mean and variance, okay? But not all of these studies are causal. In our book, Hierarchical Linear Models, we talk a lot about student social background, and we make the point that it may be, and in fact, it turns out to typically be true, that the association between student social background and outcome exists within each school and varies across schools. So so there, the key explanatory variable is at level 1. So just to kind of to make sure that we know what we're not talking about, we're not going to be talking today about the case where the explanatory variable is at the top level. So for example, if we're comparing public and private schools, we have children nested within schools, the key explanatory variable is at level 2, or we're talking about people in neighborhoods. I'm very interested in this, neighborhood disadvantage, but the key explanatory variable is at level 2. So just to be vividly clear, I want to use as a nice example, I think, a multi-site trial where there's within each school, there is a contrast between children who do and don't receive the treatment. So school 1 has a treatment group, it has a control group. School 1 will generate a treatment effect. School 2 will generate, every school generates its own treatment effect. And in HLM, we're often interested in the distribution of those treatment effects across schools. What's the average treatment effect? How much do they vary? And perhaps, what is the correlation between the control group mean and the treatment effect? So, which is an interesting kind of equity issue. Do schools with low scoring control groups benefit more? So in contrast, we're not talking about this scenario, right? Where a bunch of schools have one treatment and another bunch of schools have another. Let's say a new curriculum is assigned to some schools and other schools don't have the new curriculum. And I do want to emphasize that when the key predictors at level 2, the fixed random controversy does not arise. There's no role for a fixed effects model when you have the treatment at level 2. The schools are intrinsically going to, if we're going to study the comparison between the two groups, we have to think of the schools as being random, and the kids are random within the schools. Okay, so that's what we're not going to do. So there's a long-standing debate, and I'm going to characterize this debate through a sort of a hypothetical conversation. So an HLM person, you know, like a lot of people in the room here, I assume, and certainly somebody like me, might say, I want to use HLM. I can estimate the distribution of treatment effects using a simple HLM. I really think that's a cool idea, right? I said every school has its own treatment effect. There's an average of those. They vary, etc. But a critic, and often an econometrically thinking critic, might say, no, you shouldn't do that. You should use fixed effects of schools. You should pool the within school information and get the treatment control contrast using fixed constants for each school. And so that's the debate that we're really going to be talking about today. So the econometric argument might be, maybe there are unobserved differences between schools, school 1, school 2, all the way up to school J, that are correlated with the probability of getting the treatment. So this would have happened in a case where the fraction of people assigned to treatment differs in different schools. So we call it the propensity score, if you will, correlated with unobserved differences. And so what fixed effects do is they completely absorb all of the variation between schools and remove, therefore, any unobserved confounders, and leaving us only with the within school data. So that's been the argument. It's an argument that goes way back to panel data, where we have, even where there's individual firms or even individual people who are receiving a different intervention at a certain point in time. And in this research, the economists had said that the safer thing to do is to use or use fixed effects of the units that in that case it would be people. The random effects model generally is regarded as perhaps being more efficient, but prone to bias. And there's a test called the Hausman test for this. Okay, so now here's how our HLM advocate might come back and say, oh, wait a minute, I can duplicate your fixed effects model and, in addition, extend it by introducing random coefficients. So random effects of treatments and fixed effects of the intercept. And I can do that by centering, okay? And I wrote a paper back in 2009 called Adaptive Centering as an Alternative to the Fixed Effects Model, that shows that you, for 2-level models and 3-level models and cross-classified models, et cetera, you can creatively use centering, not only to duplicate the fixed effects model, but to create new flexibility in allowing random coefficients. However, today's challenge is, and this is really the focus of today, is that centering with random coefficients can become awkward if you have multiple levels. I'll talk a little bit more about what I mean by awkward. The centering constants become weighted averages, one problem. And if you have multiple dimensions and you're centering on more than 2 dimensions, it's definitely possible. And in my article, 2009, I show how to do it. But I noticed when I wrote the article, it wasn't that easy to do. When you went to 3-level models, you went to cross-classified models. So what we're going to do is introduce a new idea. I think this is just such a cool thing. In some ways, very simple, but it's very nice, which we call the fixed intercepts random coefficients model. And the trick is to use what Bayesians would call a vague prior for the intercept. It extends naturally and just simply to multiple levels. There are no dummy variables to create the fixed effects. There's no centering. and it's very fast computationally. And that's really the key point on today's agenda. So here's the outline. So we're going to look at the Tennessee class size study. I'm sure a lot of you are familiar with this study. It's really one of the most famous studies in the history of education research, testing the effect of attending a small classroom on elementary school students in 79 schools. And we're going to start with the 2-level HLM, which is actually, we'll see, the wrong model, but we're going to start that way just to build up our understanding. And then we're going to compare HLM with the fixed effects model. And I want to show you how we can duplicate the fixed effects. A lot of you may know this, using centering. But then I want to show you how this new approach using these vague priors sort of really simplifies the whole thing and extends seamlessly to 3 levels or even cross-classified models. So the Tennessee star, again, sure a lot of you know about this good size sample, 5,786 children are randomly assigned either to be in a small class, and they tended to be in the neighborhood of about 16 or so students, 17. And we're going to call that treatment equals 1, versus the large class, which tended to be more like 25, 26 students. And the outcome is math achievement, which has got a weird scale with a big mean of 485. You might keep in mind the standard deviation of a little bit less than 50, just so we can calibrate our effect sizes. And the goals now this is really important because people have different goals for their research. Some people might want to simply estimate what's the average effect on kids in the population of interest. But in HLM, we tend to be interested in a little richer summary. We're interested often in the distribution of treatment effects across sites, these sites being schools. So there's an average treatment effect, there's variance of those. And if we find variance, of course, we're interested in explaining the variance. Why is it that some sites have bigger effects than others? Why is it that some children have some bigger effects than others? But the summary that we're going to end up with kind of liking, I'm going to at least claim the best summary we're going to have of this data set. The simplest summary is there's a mean of 8.67 point difference between the experimental causal effect. The average causal effect in the population of schools actually is 8.67, which relative to a standard deviation of 50 is about I guess a fifth or a sixth of a standard deviation, and not trivial. But the standard deviation of the effects is quite large, 7. So a school that we would have an effect, one standard deviation above the average would be up around 15 or so. I must say though, and you're going to see that the variability in the treatment effect is not estimated precisely, and we'll see why when we get to the 3-level model. Okay. All right. So here's kind of the HLM advocates sort of first way of thinking. It's a beautiful model. It's really the theoretical model. I hope we've got just a screen share of the HLM screen. So the math is going to be the outcome for student I and school J. That's the math score. We're going to have an intercept beta 0J plus beta 1 times I. This is the funny word for it. It was supposed to be class type. Sorry, the PE got kind of wiped out, but class type. And that's a 1 if you're in the small class and a 0 if you're in a large class. So that's our experimental treatment. So beta 1J is going to be the treatment effect. We have random assignment within schools. So it's going to be the true treatment effect within schools. And beta 0J, of course, is the expected math for the people who have a 0, right? So it's the control group mean. So what this mean really gives us at level 1 is a control group mean and a treatment effect for each and every school. There's, of course, an error in the model, an idiosyncratic, kids are different, of course, within the schools. Then down at level 2, we keep it real simple. We just say the control group mean of school J is equal to a control group, the average control group mean in the population of schools, and these are the Tennessee schools, plus some school-specific random effect. And then the treatment effect in school J is equal to an average, and plus some random effect. So what we're really going to be looking for out of this model is the average control group mean, that's gamma 0, 0, the average treatment effect, gamma 1, 0, the variance of this control group means, the variance of the treatment effects, and the covariance between the control group mean and the treatment effect. And that's very interesting because as I said, it might be the case that schools that in which kids, without the treatment would not do so well. If those are the ones that benefit most, we'd see then a negative correlation between those two, and that would indicate a compensatory treatment. So that's an interesting parameter. So that's a beautiful model. It's a rich model in the sense that it gives us a lot of information. If it contains a lot of information, if we can estimate it well, that's a big question. And of course, if we discover that schools vary a lot, or that schools vary a lot in their treatment effects, then we would probably want to discover why. We could go beyond this model, and I'm not going to do that today. That's not really, I just want to stay with something simple for today, and we can talk about, because you got to have a good foundation, right? When you start looking for moderators, you want to know what you're really doing. Okay, so the standard econometric criticism is, well, unobserved confounding. Maybe treatment assignment is correlated with the intercept. Unobserved differences between schools in their mean achievements may be correlated, and that could cause a bias. And so let's be really cautious. Let's remove all of the between school variation with fixed school effects. And maybe we use a Hausman test, back this very famous 20,000 citations, tremendously widely cited. If we find that there's no confounding using the Hausman test, then the random effects model is more efficient than the fixed effects model. Then we go to the fixed effects. But generally, the economists tend to stick with the fixed effects model. So the fixed effects model is a much more simple model. It says that the math achievement is equal to an effect of some treatment T, gamma 1, 0 being the average effect in the population. There's a fixed constant U0J. So each and every school has a fixed effect, and then there's a student-specific idiosyncratic error. And the argument again is that by putting in these 79 fixed U0Js, we're removing all between school variation and therefore eliminating the possibility that unobserved confounding is causing problem in our data. So here's what you get from the two models. So when in the HLM model, we got an average treatment effect of 8.49, model-based standard error, significant T value, a robust standard error. We always give model-based and robust standard errors. They're very similar. So the T robust is very similar, and we get a gigantic variance of the treatment effects. Now here's something for you to think about. This is a very bad estimate, very biased, and you might want to ask why. Why are we getting such a gigantic and actually very biased estimate of the variance of the treatment effects here? Think about it. I'm not going to tell you the answer right now. There is an answer to this question. You can shoot it into the chat if you want, or just think about it. Okay, fixed effects says, well, no, we think the better estimate is 9.127153. And you might ask, why am I putting so many decimals in there? Well, it's to make a point later, you'll see. And the model-based standard error is really small. So we get a T of 7.40, the gigantic T. But of course, within Stata, of course, you can use what's called a cluster robust standard error. This is a Huber-White standard error. And that's much more like the model-based, much more like the HLM standard error. And so for the T is very similar. So these estimates aren't too different. They're pretty similar. Standard errors and T's are pretty similar. Okay, so we got this debate going, do we love this? I mean, I'm obviously very partial to the HLM model. It has such a rich characterization of the distribution of treatment effects. The fixed effects model says there's just this one constant. We're trying to estimate treatment effect 1.23. We're removing all the variation between schools. And so a lot of people that the debate ends there. They just say we're going to use fixed effects. Well, the HLM response has been, and this is for many, many years actually, we can replicate this within the HLM framework. We can replicate the school fixed effects model. We can do it very simply. We can just put T bar J, that's the fraction of people in school J assigned to treatment. Call it the propensity score, if you will, for school J. We can just put that in as a covariate. The rationale is the only way there can be a covariance between treatment assignment of a person and an unobservable confounder that's lurking within U0J is if T bar J is correlated. Okay, so therefore, the correlation between person-specific treatment and any school variable controlling for T bar J is by definition, by construction, 0. Okay, that's always true. It's not an assumption. It's a mathematical necessity. So the way you do that in HLM, and this was in our first edition of our book, our second edition of the book, actually it goes back to, in OLS, it goes back to Glenn Firebaugh, 1974. We have the same model at level 1. And at level 2, we put T bar, that's going to be our, sorry about the notation's kind of ugly, but it's the fraction assigned to treatment of school J, and we center it around the grand mean. And the only reason we centered is just so that gamma 0, 0 remains the control group mean. It's just kind of, you don't have to center it, but it makes it just nice to know that the gamma 0, 0 is the control group mean. And then we have to make it a fixed effects model, we remove the random effect of the treatment. We just use the constant. So controlling for this covariate in the intercept model basically replicates the fixed effects model. And if you don't believe me, look at the number what I got. Okay, now you know why I put the 6 digits in. I didn't want you to walk away thinking, well, controlling for the T bar is approximately like a fixed effects model, or it's kind of or similar. No, it's identical. Okay. We can prove this mathematically, but there's nothing like seeing the numbers when you actually run the data to really make sure, because sometimes, we make the math error, right? Okay. All right. So you might say, well, then why don't we just stay with this group mean, this T bar as a covariate? Oh, one of the nice things about it, by the way, in addition, the gamma 0, 1 is like the Hausman test. Okay. If the gamma 0, 1 is wildly non-significant, then there's no evidence that any unobserved confounders are related to treatment group assignment, because treatment's randomized at level 1. And the only way treatment can be correlated with the unobserved confounders is if it's correlated with the propensity score T bar. So we put this in the way, we're blocking it. We're sort of blocking we're blocking out all the unobserved confounders. But if gamma 0, 1 is non-significant, then, which it basically is in this case, there's no evidence of this, in this randomized trial. In some randomized and non-randomized trials, we could see a very significant gamma 0, 1. And then we know that there is this unobserved confounding, okay? But so that's a nice thing about putting T bar in. But there's kind of actually maybe 2 downsides to controlling for these level 1 means at level 2. One downside is if we put the random effect back in for the treatment, we don't get a great estimate of the variance of the treatment effects. That's one problem. And the other one is that it extends awkwardly to more complex data, three level models, cross-classified models, 4-level models. And the reason is the construction, you have to know how to estimate this mean. It sounds crazy. It's just, what does it mean as a mean? No, but you really have to use a weighted mean. And you have to know the variance components on the outcome in order to get the right weights for that. So that makes it kind of a pain. You can program that. We can certainly program. In fact, I don't know if any of you remember or know Nick Longford a while ago. In his program, he did this automatic centering. It has to be generally done iteratively. So it's not a lot of fun, and you have to do it for all the different designs, and so it's kind of difficult. The other thing is that if we get a lot of level 1 predictors, we get all these means put in the level 2, they could become highly collinear. It gets to be kind of a mess. So it's not really the optimal. But the thing I mostly worry about is I really want that variance of that treatment effect. If I put that U1, I don't know if you can see it, my little pointer, there's a gray U1. When you click on that in HLM, it comes into life, and then we can estimate the variance of the treatment effect. And we don't get necessarily good estimates. And we talk about this in chapter 5 of our book. We have a whole section on why this doesn't give the greatest estimates of the variance. Okay, so it's kind of a cool thing, but it's not quite what we want. So, that's why a lot of people, you got a question there, somebody?
Steve, this is Steve. Yeah. Just conveying a question from a user. What estimation technique is used in the HLM software, ML or REML? I believe using.
We have a choice. we do have, for the 2-level model, we have the choice. You can choose either one. For the more complex, higher level models, we stay with maximum likelihood. It's just a lot simpler. Yeah.
Wonderful. Thank you.
We can talk more, and by the way, we may want to talk, we're going to leave some time for questions. We can talk about, what are the pluses and minuses of that? Some people think, well, MLR, restricted is always better. Well, not necessarily. We can talk about that. Yeah, so using the T-bar J as a covariate kind of replicates the fixed effects model, but it doesn't extend as well because we don't get the best estimate of the variance of the treatment effect. It gets to be kind of messy with more complex designs. So why don't we use group mean centering, which is kind of a cool thing, right? You know about that. And there, we're not controlling for T-bar J, we're just subtracting it off. So all we have here is the within group deviation of your treatment assignment from your school's propensity score. And by construction, that correlation is 0. Again, it's not an assumption. It's just, you can just show very easily. It always has to be 0. There's no way that knowing, whether you're in a, let's say, knowing that Lee is attending a really terrific school doesn't tell, or let's say Lee and I are both attending a terrific school, gives no information about whether Lee is doing better than me or I'm doing better than he is. No information in there at all. So there's no correlation. So what do we do? Well, in HLM, now we still have math achievement, child I school J, we still have beta 0 J, but now we're taking the treatment variable and subtracting the group mean, the mean dot J. So that's the mean. This is the propensity score. It's TIJ minus the propensity score, basically. Beta 0 J is now actually the mean math achievement school J. It's no longer the control group mean. And this cannot be correlated with unobserved level 2 variables. So that's going to solve the fixed effects challenge, right? To replicate, we have beta 1J equals a constant. We don't let it vary. That's a strong assumption, but that's assumption fixed effects model, that there's no variation in the treatment effect. So we're going to just try to replicate. And here's what we get. I just wanted to show you the numbers again because just to check and see, we get the same thing. Okay, so we got 2 ways of replicating. And the nice thing about the group mean centering is that it does extend in the sense that it gives us a good estimate of the treatment effect variance. So that's a useful thing to know. How much heterogeneity is in their treatment effect across schools? Very important, because a mean is not very informative if there's a lot of variance, right? Yeah, okay, on average this thing works, but like a third of the kids are, repeating grades and having a lot of trouble. That's not a good thing. Yeah, maybe some people are really excelling, but other people are getting hurt. If that's true, if that's true, we want to know that. We don't want to assume that there's a fixed effect treatment and be married to that assumption, right? We need to know whether that's really happening. So, okay, the downside of the fixed effect of the group mean centering. So it has an advantage over using the T-bar as a covariate. The downside is, again, it extends awkwardly to 3 levels and to multiple levels of nesting below the top 2 levels, cross-classified, mainly because getting the T-bar J's right getting the propensity score weighted correctly, the weighted mean, getting the right weighted mean, and especially in cross-classified where you have to have double centering. And my 2009 article talked about that. I wasn't very comfortable with that. I said, yeah, we can do this, but it doesn't look like a lot of fun. It looks like it's a lot of work and very challenging. So, all right, so that leads us then to this sort of vague prior. This is kind of the main idea for today, right? This is really what we're talking about, which is the third way that we can, within HLM, we can replicate the fixed effects. And then what we want to do is we're going to show how to extend it and generalize it in very creative and interesting ways with combinations of fixed and random effects. Okay, that's the whole idea here. So what we do is we say, in HLM, we say, well, the variance of the intercept if we're letting it randomly vary is tau 0, 0. And the vague prior says, well, that tau 0, 0 is going to be an arbitrarily large constant. And what that's really saying is that I don't know much about the intercept. if I'm going to a school I've never been to before, and I know in the population intercepts have gigantic variance, then I have no prior information about the school, which is saying that the inverse of the variance is approaching zero. Okay, so the inverse of the variance is called the precision. So in a Bayesian sense, how precise would be it if I estimated that a particular school had the same intercept as the average in the population? Tau 00 to the reciprocal of tau 00 would be the precision, the inverse of variance, right? And if tau 00, if the inverse, I'm sorry, the precision is zero, it's saying I have no confidence whatsoever that this school intercept is near the population mean. Therefore, I'm not going to do any shrinkage at all, which is what we do in HLM. We use shrinkage toward the mean because that can remove a lot of noise. And it turns out that you end up with it replicates the fixed effects model. Now, I've given you a very short, probably not very satisfying explanation for why this works. I have an appendix where I can show you a little more detail if we have time at the end, and I can send these out. We can talk about it. But this idea that when you have, if you're a Bayesian and you have a vague prior for something like an intercept, that you're going to replicate the fixed effects model. This was pointed out by Lindley and Smith in 1972 in a classic article in the Journal of the Royal Statistical Society. It's showing my age. This is one of my favorite articles. It still remains to be one of my favorite articles that's ever been published. It's a great article. Okay. So again, leaving aside that I haven't given a wonderful explanation for how this works. Just let's assume we do it. Let me show you how to do it in HLM. So in HLM, you go to other settings, estimation settings, and you just press this little button, fixed intercept random coefficient. I can fix the intercept. And if I want, I can let the coefficient be random. Just check that box. That's all you have to do. No dummy variables. There's no centering whatsoever. Okay. And so we get the following model. The level 1 model looks like it always has. We have the, or not always, but the original one. Beta 0j is the control group mean, school J. Beta 1j is the treatment effect. The beta 0j's are being set equal to U0j, which is now a fixed constant for each school J. This is just a fixed constant. Okay. I mean, you could say, well, it's randomly varying with infinite variance, but it's a fixed constant. And the treatment effect is being held constant at gamma 1, 0. So again, no centering, no dummy variables. You can have hundreds and hundreds of schools, thousands of them, no dummies, no centering, and you see the result. Okay. All right. Perfect replication of the fixed effects model. And you say, well, we're beating ourselves up. Why don't we just use the fixed effects model? Why are we trying to replicate? Because we want the virtues of fixing the intercept, but we want to add the value, the utility of estimating the randomly varying treatment effect. And we also want to extend this. The fixed effects model also doesn't extend well itself. I'm going to try to explain why I say that. In this paper with Howard Bloom and Michael Weiss in 2015. Oh, Kristen Porter. Oh my God, I left her name out. I got the references all at the end of this, so she will be saved. We can then click. This is the same model, but now we just clicked on the U1 so that now we have a randomly varying treatment effect. Okay, so we're fixing our intercepts. We have the randomly. So we're absorbing all the variability between schools. We've got a randomly varying treatment effect. By the way, only within school information is used to estimate this. Okay, so that's cool. We're not using any between school information. And here's what we get into the bottom line here now. And interestingly, our point estimate of the average treatment effect actually looks a little bit more like the original HLM. And our model-based estimate of the standard error and our Huber-White are very similar, which is kind of nice. I like that. I like it when the model-based is similar to the robust. Okay, it doesn't mean my model's right, but maybe at least means that my model isn't causing like grotesque biases or distortions. And I'm getting a very much similar variance. So really, and the reason they're similar is because because of the Hausman test, the simplified Hausman test. You know, there was no correlation between T bar J and treatment and the propensity scores. So that's why we're getting very similar results here. But that's a nice thing you can do. You can check your theoretical model, your HL model, by using this fixed intercept random coefficient. That's one of the things you can do. Oh, I don't know if anybody put in the chat. Does anybody, hey, Lee, did anybody put in why this 17 point whatever squared variance is horrible?
No, I think that
nobody had that. Oh, I thought maybe you guys would have figured that out. Maybe you did, but you're too shy. That's what I often find. People don't want to say stuff. But, but it's more fun to take the risk and try something. Okay, so the reason is we're not really thinking clearly about Tennessee star. The fixed effects model wasn't based on clear thinking, and none of the HLN models were, okay? Because in each 79 schools, again, we got the 5,786. This is a 3-level model. These kids are nested within classrooms, okay? So we got kids in classrooms. And by the way, the teachers are also being assigned to the larger small school, which is a very wonderful feature of this, because it's not like just the teachers are teaching the small classes are better than the teachers are teaching the large class. They were randomly assigned, okay? And the kids were randomly assigned. It's incredible. It's an incredible study. And not taking the 3-level structure into account can cause some problems, some major problems. Not all problems. Some things are okay. You'll see. So we really want to go to the 3 levels. So now this is where we really see the benefit of the vague prior, because it's just so straightforward and it generalizes so beautifully, and we don't have. I get 79 schools. I don't want to put 78 dummies in my model. I'm lazy. I don't like that. I don't want to do the group mean centering, knowing that I have to figure out the correctly weighted mean and all that stuff. So we're going to look at 3-level models, and then that'll wrap it up. Theoretical model of vague prior for the level 3 intercept and a fixed intercept random coefficient model. So here's the theoretical model we probably should have been using. So the math achievement for student I in classroom J school K is equal to a classroom mean pi 0 JK plus error. The classroom mean is what then varies. There's the control mean in school J is now the average of the classroom means in the control group. And then there's the treatment effect in school J. And notice its class type is actually not a level 1 variable. It's a level 2 variable, because everybody in the same classroom has the same value on that variable, right? We really need a 3-level structure. This is why we screwed up our variance estimate, by the way. So at level 3, we have the control group mean, we have the treatment effect. And because we didn't have the RO0JK, and what happened to our variance was that the variability between teachers was confounded with the treatment effect. That's what happened, and blew it up. Okay, so that's why what we see now, we see a pretty similar average treatment effect. We got a standard error model-based, robust, very similar. But now the variance estimate is 7 squared instead of 17 squared, because we controlled and removed the teacher variance. That's the answer to the question. The classroom variance was confounded with the treatment effect variance, and so that's why the 2-level model was messed up. Now the P is it's a large estimate, but it's not significant at the usual levels. The reason being, there aren't that many classrooms in each school, so it's hard to get a reliable estimate for each and every school of the treatment effect. Only 3 or 4 classrooms per school, okay? These are kindergarten classrooms. Okay, so at level 3, we go up here and estimation session, click on the fixed intercept, same thing we did before. Here's our model now. It's changed because now down at the top level, beta 00K is equal to a fixed constant for each school plus an average treatment effect, no random variation. So we don't get any tau out of this. This is kind of just, now what this is it's interesting. This is a fixed effects model with a 2-level structure, students in classrooms sitting below the fixed effects of school. Okay, you don't see that in econometrics, but it's very useful. Particularly if you're interested in heterogeneity, we put the random effect in of treatment at the level 3. Now every school has its own treatment effect. Whoops. And we get a result that actually looks like our theoretical model. This is our best estimate, probably, I think, that I could get without adding covariates the best estimate of the average treatment effect, T is, because the standard errors are very similar to the robust. T is around 3.6 or so. We get a variance estimate. Those are pretty similar p-value. So you can kind of go with either the first or third summary. I don't like the vague prior. And then actually, the fixed effects model for our purposes can cause bias. We can talk about how that works. In fact, let me just quickly do these conclusions. We're going to run out of time and have no discussion. So we like the theoretical model, and we prefer it if the level 3 random effect is non-informative, meaning it's not correlated with any unobserved covariates at level 3. We can use the group mean effect. We can just put the group mean in of the treatment at level 3 to just test that. And if we see nowhere near an association, then we kind of like this theoretical model. Putting the group mean gives us an unbiased estimate under our assumptions of a random assignment and so forth at level 1, or level 2, I should say, level 2, very much important, level 2. Gives us an unbiased estimate of the treatment effect, but not such a great estimate of the treatment effect variance, awkward if there's many level 2 predictors. Group mean centering gives us the nice treatment effect variance, challenging though to extend it to the multiple dimensions. The vague prior, which is what we're kind of showing today, gives us the unbiased estimate of the treatment effect, and the treatment effect variance extends simply to multiple dimensions and no dummies and no centering. It's computationally trivial. Okay, so that's it. I've got caveats. Oh yeah, we are focusing on the mean and variance of the treatment effect across sites and schools. We could also, a different thing to do, if there's heterogeneity of impact, we could estimate the average of treatment effect on a population of persons or a population of teachers. This is something we're going to get into in another webinar. We talk about how to use weights to target different populations, keeping in mind that we're currently looking at a distribution, because each school has its own treatment effect. We're looking at that distribution. And then we've got a bunch of references that you can get. We'll make these available to you. And there is a little appendix that shows you how this vague prior works. I think I want to stop now just because we got a little bit more time for some questions and some discussion.
Steve, this is wonderful. I am monitoring the chat, and so far there has not been any new chat messages. Also,
hey, is anybody home out there? I hope I'm not talking to myself.
I'm really curious about whether this extends out to the case where the outcome isn't necessarily a continuous variable. So let's say if there is because you know me, I deal with discrete variables all the time, and for these discrete and limited dependent variables, would tricks like this work?
It will. Now, there are some caveats that we should think about, and maybe even have another webinar about fixed effects, like say with a fixed logit model. What does that do for us? There's some interesting new references on it, but basically it will give you that. It will give you the same as the fixed effects logit model, and you can extend it. And of course, the reason I say this is as you know, in a nonlinear model, when you have more variability of the intercepts, it has an effect on the coefficients. Right, in a normal theory model with continuous outcome, the mean and variance are independent, right? But so it does change the interpretation somewhat, I think, of the average treatment effect when you have a fixed versus random coefficient. So we have to be careful about interpretation, but I don't see why I haven't done it, so we should really look at this. We should look very carefully at this, but I see there's no intrinsic reason why this wouldn't apply.
Great. There are questions coming in. One question is, can you talk about extending this approach to repeated measures within persons?
Yeah, well, actually, that's a very natural application, because let's say that I have, the extension is done. It's there. It's just the same thing. And I've used this model on that. Very nice. Some of the economists would say, let's use fixed effects of persons. But they could have different slopes, like growth trajectories. but we're removing where everybody is basically being, what that really does is it centers everybody around their mean of their age. Let's say we're using an age outcome growth curve. And when you put fixed effects of people in, you're effectively centering age around that person's person-specific mean age. And you can get a linear trend or you can get quadratic or whatever. So some people like that model for the same reason. If there's a treatment scenario going on where people are getting a within subjects treatment, it's especially interesting because some people may have more observations than others. And you may not want those people to get more weight. You may want to be generalizing to a population of people and looking at a distribution on that population of treatment effects, in which case this would be a very useful way to go. So this applies it very simply to the, it just seamlessly to the two-level structure where the first level are occasions and the second level are people, as well as where the first level are kids, let's say, or people, and the second level are groups. Absolutely.
Wonderful. Thank you, Steve. And on the question and answer box, we're seeing more questions. The first question is, if we want to add level 2 covariates, could we use the fixed effects approach?
And that's a good point. And no, you cannot. And that's also true of any fixed effects situation. You've completely absorbed the variability between schools. And so there's no scope for any level 2 predictors, which is kind of what I was saying at the beginning. That's why we're not talking about that case. Now you can have interactions. Here's an interesting point. You can have interactions between school level and child level. Let's say you have schools that are located in urban versus rural. You can interact urban versus rural and put it into the level 2 model, but you wouldn't get the main effect of urban versus rural. You still get the interaction effect, but the main effects are completely absorbed by those fixed constants.
Steve, there's another question concerning unbalanced classroom sizes. The question is, how worried should we be about unbalanced classroom sizes where the treatment is at the classroom level?
Yes. Yeah, okay, so that's something I'm actually, Dan Schwartz here at Biostatistics students and I are just submitting a paper on that topic. Of course, the class size here is, of course, the treatment in this particular case. But I think you're asking about a more general case. Let's say that we have teachers who are trained to teach in a certain way versus not in the same school, and the classroom sizes are varied. So what you have to ask yourself is, are the classroom sizes informative? Is there likely to be a correlation between the classroom size and unobserved characteristics of the schools? That's what you're going to be asking for. Or if there's no school, usually it's going to be right. The classrooms are in schools, but and to guarantee that can't happen, we use weights at 2 levels in HLM. We use weighting, and we're going to have another. I think the next webinar is going to be more on invariance estimation, trying to get that right, and then we're going to have another one on weighting. So we're going to talk about that one. It's a little bit tricky, but HLM is quite robust. By the way, HLM is more robust than the fixed effects model when it comes to classrooms having unequal sample sizes, because the fixed effects model will tend to put more weight on the biggest classrooms, and if they have extreme treatment, if they're bigger, if the treatment effects are correlated with class size, then we may be causing distortion. And we talk about that. Now, I'm assuming that again, it depends on the level of generalization. This is tricky. See, in Tennessee, as I said, you could generalize the population of kids. You can do the weighting, classrooms, or schools. We think schools is a natural because each and every school produces a treatment effect. Yeah. So the answer to the question is, we can eliminate any possible confounding having to do with different sizes by using weights. The penalty we pay is that we get larger standard errors. The weighting, the variability of the weights is going to increase our standard errors. But it's very worthwhile to know how to do that, because at least if nothing else, is a check, a sensitivity analysis.
We also have another question, Steve, and this is about estimation It's from the same participant that asked about maximum likelihood versus restricted maximum likelihood. And the question is, how does HRM use the EM algorithm? Does it use it at all? How is it implemented?
Yeah, we use the EM algorithm actually in conjunction with what's called Fisher scoring. And the combination we iterate, when we have full, at least when we have full information maximum likelihood, we use 5 EM iterations, and then we have a Fisher iteration. And the reason is the EM iterations are very reliably within the parameter space. They make small steps toward the solution, but they can be slow. And if things are going well, we can dramatically speed up the iterations by using Fisher scoring. We used to care about that a lot more than we do now, because computers are so fast. I mean, it could be 1,000 or 10,000 EM iterations, and for the sets I'm having, we don't care. Now, if you have these gigantic data sets, a certain, very complicated model, cross-classified with lots and lots of levels or something, then the EM is can be quite slow. But we like the combination, because the problem with Fisher scoring is it can push you out of the parameter space into negative variances or correlations greater than 1, or things that you don't want to see. So we always stay in the parameter space with our EM, but we maximize the speed by having the alternating Fisher scoring. I'm not sure that answers the question. You were saying, how do we use EM? It's pretty standard, actually, at this point. It's in our book, actually, in chapter 14. It would take me a while to show. We have a complete data estimators that are very simple. And then we take the conditional expectation of those complete data MLEs, given the observed data, posterior expectation, given the observed data. And we substitute that into the complete data formulas. That's pretty much standard for EM.
Now, the next one is a more, I would say, philosophical question. And it is, do you think causal conclusions can be reached from observational studies with the use of HRM or other methods?
With assumptions, right? With assumptions. So the beauty of random assignment is, the assumption, right? If you go back to the, I'm an advocate, or an adherent to the potential outcomes view of causal inference, that, if I'm assigned to the small class, I have a certain outcome. And then if I had been counterfactually assigned to the large class, I would have had a different outcome. The causal effect for me is the difference between those two counterfactual outcomes. We don't observe those. We can estimate the average of those by comparing people who did and didn't get the treatment. If those two groups are exchangeable, meaning that their potential outcomes don't predict their treatment assignment, okay, are uncorrelated with the treatment assignment. So the beauty of random assignment is that assumption is satisfied by construction, by randomization. And so what's generally happening in the non-experimental observational studies is we're trying to do as if randomized. We're saying, well, within subsets of people who are very similar on their covariates, it's as if they were randomized. And that can be a very strong assumption. In some cases, it's a very plausible assumption. I think it depends a lot. I've seen some studies that very, very convincing, probably the most convincing observational study that we have, that we know of, is the effect of smoking on lung cancer. We never randomly assigned people to smoke larger numbers of cigarettes. We did that with animals, by the way. We did it with people, but the observational findings were such that it was impossible to have any plausible scientific explanation for the association. Just could not be explained by any covariates anybody could think of. And if there were a covariate out there that would reverse it, it would have to have an effect that's like many times larger than the biggest confounder we could ever find. And that was enough for the Surgeon General to put to stamp on the back of the cigarette package that this is cause of cancer. So I think it varies, but it's always under assumptions. So the scientific question is to evaluate those assumptions. They have to be evaluated. They have to be stated. I don't know. I'd be interested to know whether the person who asked that agrees philosophically. If you want to type in what you think. Sorry, I can't hear.
Steve, so we still have a couple questions. I know that we're short on time, but there's one question, the one that actually came in last, that is also a more philosophical question that has to do with getting your thoughts on Yuta Pearl's approach using DAGs and how it might be used in conjunction with HLM.
Well, certainly it can be. I mean, you can, so what HLM is sensitive about your design. Do we have a multi-site trial? Do we have a cluster randomized trial? Do we have some other more complicated sort of multi-site cluster randomized trial, which is kind of what we see in education? And as soon as you know what your design is and where your treatment is and what your outcomes are, you can derive the HLM model straight away, right out of the potential outcomes. It falls right out. I'm going to write a book about this. Actually, you can write down the potential outcomes, and you can write down the HLM model as being with no assumptions. Now, the assumptions to estimate the model, you have to make assumptions there, and that's what we were talking about today, about observed confounders and all that kind of stuff. So, so the HLM framework is mainly within the experimental. It's a flexible way of responding to a lot of different experimental designs and different kinds of outcomes, like different, as Lee was saying, different kinds of scales of measurement and so forth. So it's really not different from any, in that sense. It's just a more realistic way, I believe, at least, of bringing the design explicitly into, like we have here. We have kids, we have classrooms, we have schools. The classrooms are the unit of randomization that really matters, and the kids are creating extra uncertainty. And below that, we have the schools, and we have the unobserved confounding. So the design. So we fit the model to the design, and when you fit the model to the design in a rich way, you tend to come up with an HLM model. So as far as Pearl goes with the DAGs, I mean, I think it's often very, to me, heuristically useful to look at those things. I'm not a big fan of trying to make a list of all the possible colliders and all of the different ways. Basically, we're using some kinds of assumptions, strong ignorability that have to be met, and that's a more parsimonious way of defining what our assumptions are. But I think it could be very useful for people trying to understand, well, what could be, how could we be violating that assumption maybe if we have this set of covariates? So, yeah.
Thank you.
Then mediation, there's a mediation framework coming out of Pearl. It's also very interesting. Guanglei Hong is at Chicago has really done a lot of interesting work, or Imai, Kosuke. We can do those mediation. We've done a little bit of mediation work in HLM. We can talk about that maybe another time. I know, that's a big issue.
Right. Thank you, Steve. So there are two more questions, both of which I believe could be clarifications. One question has to do with status cluster option. And do you have any thoughts about that? And the other, I believe, could be a very simple clarification. That is how HLM8 deals with missing data. It's a very broad question. So perhaps that is something that is worth another webinar.
Yeah, because just on that one, so we have this model-based imputation within the new version of HLM that is kind of, I think, beautiful, because you write down your model. HLM looks through your data set, figures out where your missing values are, creates a big multivariate model, estimates the joint distribution of all of the observables, and then randomly draws from the posterior distribution, creates multiple mutations, analyzes those, gives you an answer. So it does all of that stuff automatically. And it's a very, very, I'm a big fan of multiple imputation for missing data. We should talk about, why and when. And so that's the Cadillac really for me of how to do it. You can do weighting. Of course, you can also do non-response weighting, and there's other ways to think about it. But just as analyzing the complete cases, people who have complete data is probably not a very good idea, right? We know that from Little and Rubin, from others. So we can use the Little and Rubin kinds of ideas and just bring them into the multi-level framework. Now, there was a question just before that, Lee, that I didn't answer because I forgot.
it's about the cluster option in Stata.
Oh, well, I was running that, and I showed you those. They look pretty similar to ones we have in HLM. I am worried about controlling for clustering in a fixed effects model. Actually, there's a literature on this. This is a problem, really. If you have many groups, and you have many, many fixed effects, it's not at all clear that those robust standard errors are going to work. So the model-based standard errors may be very helpful in this particular case if you have a good model. You can't always assume that the cluster robust standard errors, you see what I'm saying? Cluster robust standard errors are best when you have a small model and a lot of level 2 units. That's when they work really, really well. They don't have to have that many units if the model isn't too big. We did a simulation study, 25 or 30 level 2 units seemed to be very fine, no problem, but less than that wasn't so good. But when the model gets big, and I mean, in this case, big because you have a lot of fixed effects, then I think there's a lot of problem. People don't discuss this. They write their papers. They say, we did our fixed effects model. We did our cluster robust standard errors. And then that's it. They say, we're golden. We get into heaven, we can get into heaven with that. So we need to look more deeply into that. I've been reading some more articles lately that are raising questions. And I think they can be fixed. I think the cluster robust standard error can be corrected in some ways. There seems to be some research on that, but it's not as obvious as it seems.